Welcome back to part 3 on polynomials and their graphs. We need to be able to graph polynomial functions. We have studied how graphs of first, second, and third degree polynomials can be graphed using shifts. So what should we do with the rest of these polynomials? This section will focus on this very important goal of graphing polynomials that are of higher degree and have very unique behavior. To graph polynomials, if you can't use shifts, use the following steps. Step 1, find the end behavior, and we'll talk about that more shortly. Step 2, find the zeros and their multiplicity. You might want to make a note right here that says zeros are the x-intercepts, and multiplicity is the power. You might also be familiar with this as not a power, but an exponent. So you might hear someone say raised to the power, so that's what that means, an exponent. Step 3 says test points. Not necessarily for this class, but you can use test points to be more accurate. And if you've used them before and you know how to use them, then you're welcome to. And then you graph it, and we'll talk about how to do that shortly. Let's start with the end behavior of a polynomial. The end behavior of a polynomial is to study the changes in y values as x approaches infinity. This means when x becomes large in the positive direction. Or x approaches negative infinity. X becomes large in the negative direction. For any polynomial, the end behavior is determined by the leading term. The degree n and the sign of the leading coefficient a sub n will tell us all we need to know about the end behavior, which is crazy that just that first term will be able to give us so much information. So the end behavior can be determined by this leading coefficient, as I mentioned earlier. Let's take a look at two situations where you would have an odd degree polynomial. When you have an odd degree polynomial, you will have your end behavior on opposite sides of the x-axis because your polynomial crosses the x-axis and then continues on. And that's from a previous video. If you want, you can go back and watch that again. If you have a positive odd degree polynomial, the end behavior on the left will approach negative infinity. And then we don't really care in this particular video what happens in the interesting area of the graph. Because that's why it's a dotted line, because I don't really care at this point what's actually happening, how many times it's crossing the x-axis, etc. I just know that at the end behavior will be positive as x approaches positive infinity. And I know that my end behavior goes downwards toward negative infinity in the y direction as x approaches negative infinity. So let's write that formally. On this side, on the right side, as the polynomial moves upward as it goes toward positive infinity, we would say as x approaches positive infinity, f of x approaches positive infinity. And down here in the bottom left quadrant, we would say as x approaches negative infinity, f of x approaches negative infinity. So this would be an example of a polynomial f of x where your leading coefficient a sub n a sub n is greater than 0, meaning it's positive, and your x term to the n is an odd number. N is odd. Now let's take a look at a negative odd degree polynomial. Remember, when you have a leading coefficient that is negative, it means it's flipping the graph about the x-axis. It's flipping it over vertically. So this would be an example of f of x equals a sub n x to the n, but in this case, a sub n is less than 0, and n is still odd. Notice that I will try and draw this graph fairly similarly to what I had before, but now my function is approaching positive infinity on the left. It'll wiggle through some interesting shape based on how many exponents I have, and then it will leave on the right toward negative infinity. So we would say on this particular graph, as x approaches negative infinity, f of x approaches positive infinity. Because as if we make our values get smaller, the function curve moves upward, so it's getting bigger. As we move to the right, as x approaches positive infinity, f of x, the curve f of x, approaches negative infinity. Now, I really, really, really implore you, I really ask that you try these a few times, because this is some new stuff. A lot of you probably haven't had the little arrow symbols before that say approaches, but this is really going to help you when you're graphing the polynomials. Let's take a look at even degree polynomials now. With even degree polynomials, if they're positive, we have end behavior that is the same on both sides, and it will be opening upwards. And we might have some interesting curvy stuff in the middle, but our end behavior to the far right and to the far left has positive moving upward behavior. In this case, we would say as x approaches negative infinity, that's moving to the left from 0, f of x approaches positive infinity. And hopefully you're seeing that the behavior on the right side of the graph is exactly the same, which means that as x approaches positive infinity, f of x approaches positive infinity. So in this particular scenario, we have f of x equals a sub n x to the n, where a sub n is greater than 0, it's positive, and n is even. Now, if you have a negative even degree polynomial, then your function will do the same thing. The end behavior will be the same on both sides. However, the function will be flipped downwards because it's negative. So your function is now opening downwards instead of opening upwards. So we would say as x approaches negative infinity, f of x approaches negative infinity. And as x approaches positive infinity, f of x approaches negative infinity. You can think of all the f of x's approaching something as your y values. And I'm emphasizing this because I know how weird this can look the first time you see this notation. Notice that f of x approaches positive infinity. It moves upward on both sides for positive even degree polynomials. And if your polynomial is even and negative, your f of x, your blue curve, the curve that I just sketched, it is moving downward as x approaches both positive and negative infinity. We're looking at the far ends, the extremes, not the interesting dotted line in the middle. That's not what we're looking at right now. So I'll finish up this last statement here. This last one is even degree and negative. So f of x has the form with the leading coefficient a sub n x to the n, where a sub n is less than 0, so it's negative, and n is even.